So today we're going to be talking about the various ways in which you can misuse Cassandra and not get the scalable performance that you're after. And I've probably done most of these and then had to redo things in my experience with Cassandra, especially from moving from a relational background. And a quick introduction, though Christian did it well. So I work as a technical evangelist. Most of the things I'm going to speak about today I've inadvertently done at Sky. I spend my time doing talks and building example apps. I also maintain a testing framework for Cassandra, which is how I keep my coding skills sharp. So as Christian says, we'll be getting to questions, but if we don't get to your question, then I will write up a blog at the end and try and answer them all. Or if you think of questions down the line, then feel free to ping me on Twitter. I'm more than happy to answer questions later on. So here's the list, okay? I'm not going to read them out, but one thing to notice is most of the things that we're going to speak about today are actually Cassandra features. So batches and the driver retry policies and tombstones and secondary indices. So I'm not going to say that the use of them entirely is anti-patterns. They're just the features of Cassandra that most people end up making mistakes with and using them slightly incorrectly, not getting the kind of scalable performance that they move to Cassandra for. But we're going to start off with joins. Because when I first moved and started to use Cassandra as a distributed database, the first thing I noticed was, hey, where are joins? Where's group by and aggregates? And there's a very good reason why Cassandra doesn't support these features. So when I was trying to build systems with Cassandra, I'm after two things, and that's scalability and performance. And when you combine those two things, what it essentially means is that if I start off with a small application, say 3 nodes of Cassandra and a few instances of my application, and I'm getting 10 millisecond response times, I want to build a system which, as I scale it up to the tens, the hundreds, if not the thousands of nodes, I still want to be able to get those 10 millisecond response times. That's what I mean when I say scalable performance. So there are certain, say, lack of features, you could say, in Cassandra that, one second, sorry. So there are certain features missing in Cassandra because you can never implement them scalably. And one of those is joins, and another is aggregates. That's because if we ever tried to make Cassandra do anything which scan the cluster, then that might work for a small cluster, but never for a large cluster. However, what people do when they move to Cassandra is they say, okay, Cassandra won't do the join for me, so I'll just do it myself inside my application. I've definitely done this one. So I tend to be able to explain things better and learn things more easily when I do it via example rather than just theory. So throughout all of the anti-patterns that we're going to speak about today, we're going to use this common example. And it's one that a very similar system to what I built at Sky. So essentially what we're going to do is we want to store everything our customers do. We want to store if they log into our site or they log into one of our mobile applications, or perhaps if they actually come into a physical store. We want to store what staff members are associated with that event. You can imagine how this could be used. It could be used if a call center, if a customer rings up and complains, or it could be used for analytics to see what a customer's done historically. Okay, and our assumption is that as we build and get more and more customers and they do more and more things, we're going to have to scale this system. We're going to have to add more nodes to our Cassandra cluster. Okay. And if we tried to model that, quite traditionally, we'd probably end up with a couple of tables, okay? We can see 2 distinct entities there. We can see events, but we can also see the store. And by the store, I mean, did they come via our mobile app or our website or our physical store? And you might think, oh, I want to model it like this. I'm used to modeling it like this. But what we're going to do is try and work out what will happen in Cassandra if we do it this way. And I quite like to explain things with animation. So I'm going to assume that you know a bit about Cassandra, you know about replication and consistency, okay? So when you come to read this data, let's pretend we have an 8-node Cassandra cluster, so quite a modest cluster, and we have a replication factor of 3. what we're going to do when we read this, we want to get an event out of here. So assuming we're using one of the, say, the data stack drivers, it's going to speak to a coordinator. You're going to specify a consistency when you execute this query. We'll say it's quorum. Assuming that the coordinator wasn't a replica for this data, we'd end up having to speak to an extra couple of nodes, okay, to meet that consistency. So we need to speak to 2 out of 3 nodes, okay? And then obviously the coordinator will respond back to the driver when that's complete. But of course, because we've tried to normalize our data, we need to go to Cassandra again. So what's going to happen here is we're going to have to issue a second query. Now, chances are the driver is going to speak to a different coordinator because it load balances around them. And if we're executing this at quorum again, then we're going to have to speak to yet another 2 nodes. And what you'll see here is if you actually try to do client-side joins, then you end up needing a vast number of your nodes to be up and responsive to actually, achieve one user transaction. So apart from the fact that you're adding latency because you're going to the cluster twice, you might think this is okay because Cassandra is probably quicker than some of the databases that you've come from. But still, this is 6 out of 8 nodes. And this is actually probably the best case for client-side joins because it's what I classify as a one-to-one mapping. We had one customer event referring to one store. So that means that we only needed to do 2 queries. But what normally happens if you continue to model your data like this and do client-side joins is you fall into a more general anti-pattern, which I classify as multi-partition queries. So you end up doing what some people call multi-gets. So imagine that if one customer event, mapped to multiple staff members or multiple stores. And that's where we're going to end up doing multi-partition queries, which are really going to hurt performance and they're really going to hurt availability in our applications. So let's say that we had a new requirement come in for our customer events, and we want to associate multiple staff members. So here I've changed the table so that actually it's a set of staff members are associated with this event. And we want to talk about some of the staff members, say their job title, jokingly their favorite color. What type of queries is this going to lead to? It's going to lead to queries that look like this. So after we get back a customer event, we're going to end up doing a multi-partition query to get the information about all the staff members. Sorry, did someone say something? No. Okay, so what we're end up going to do is this multi-partition query. And these are really bad for a few reasons. One is because we have to speak to so many nodes again, so very similar to the client-side join. But the other thing is, if a very small part of this query failed, let's say that we had staff member 1, actually the node was down or was slow or overloaded, but we actually got the information back for staff member 2, 3, and 4. We're going to have to retry that entire query, okay? And that means that we're going to, while things are going badly when perhaps queries are slow, we're actually going to overload our cluster even more by retrying large queries. And what we're actually going to do is circumvent the token-aware load balancing policy in the modern drivers. That's where it tries to communicate with a node, which is a replica for the partition, which you're trying to either read or write. As soon as we do these type of multi-partition queries, the driver has no chance. It might be able to go to the partition for, say, staff member 1. That's going to be a different replica for, say, staff member 2, 3, and 4. So rather than look at animation for this, we're going to start looking at trace. And a tool which I find absolutely invaluable for doing data modeling locally is the Cassandra Cluster Manager. What it is, if you haven't used it, is it's a way to spin up small clusters on your single development machine. So rather than having a single node Cassandra cluster, it enables you to say spin up a 3-node or a 6-node. And it cuts down the memory usage and the number of threads, so it won't be as resource intensive. If you haven't come across CCM before, then you can go to the website. It's on GitHub. I can send out the link after this. But there's also a course in the DataStax Academy about installing and configuring Cassandra. and it has a whole video about CCM, so you can go and learn about it there as well. So what I've done for the examples is I've spun up a 6-node cluster locally, okay? I wouldn't normally run this larger cluster. I'd normally stick to a CCM 3-node cluster for most of my development purposes. And what we're going to do is we're going to insert some data. We're going to look at, we're going to insert some staff members. So we have 3 technical evangelists here. You know, we've got CH Beatty, Luke, and John. And we're going to have a quick look at the trace for if we did the query select star where name is in. So this is a multi-partition query, and we're going to go to 3 partitions. So this is what would happen if we associated these 3 staff members with, say, a customer event. Now, I'm not expecting you to read the trace, don't worry. What I highlight here is the column with the IPs of the node, so the one on the middle column. And what you'll notice here that I did this query at consistency level 1. I originally did it at quorum because I wanted to keep it as close to the animations as possible. But if you do this query at quorum, then there was no chance of me ever fitting this trace on a slide. But what you can note here, we're down to a 6-node cluster here. But to do this one query, we needed 4 nodes to be up and responsive. So you can see how likely it is that this query can fail. And we've already talked about how retrying that query is expensive. Whereas if we did this as, you know, even if we did want to query like this, we should be doing it as small individual queries so we can retry them. However, the best solution is, of course, to denormalize. And if you haven't got onto Cassandra 2.1 yet, then you're in for a treat because user-defined types in Cassandra 2.1, I think for me, make me happy about denormalizing. You know, before user-defined types, I might have had some concern about adding column after column after column to my tables and then duplicating. But now I pretty much can see, you know, when I do my data modeling is when ordinarily I would have a different entity, say store or staff. Rather than create a separate table, what I like to do is create a user-defined type, and see we can use them directly inside the customer events table. And this is really powerful because now when we query our customer events, all of the information about store and staff are all going to be stored sequentially on disk, and we're going to be able to read it very quickly. Okay, and we're not going to have to go to multiple nodes in the cluster, or we don't even have to go to multiple nodes to reach our consistency. So before we move on from client-side joins and multi-partition queries, I'm going to show one slightly more subtle example, okay? So if you've ever done any time series data modeling with Cassandra, you've no doubt come across the concept of bucketing. If you think back to our data model that we've been looking at, our customer events table, you know, you'd probably notice that the customer ID is the partition key. And thus all of the events for a particular customer end up in the same partition and end up on the same node. Now, eventually this could get too big. So if our customers are very busy and they manage to do hundreds of millions of events and stay with us as customers for a long time, eventually we'll want to spread their data across multiple partitions. So what we typically do there is add a time bucket. And if you look at the primary key is the important bit here. What we've done is we've added something to the partition key. So it's not just the customer ID now, it's also the time bucket. And we could make this the day of year or the month or the year. And this basically means that we would move along, we'd start using different partitions. But the problem that you can actually fall into here is if you make your partition, your time bucket too granular, let's say you really wanted to future-proof your model. Let's say you made it second. What you can end up doing is forcing yourself, when following a good pattern in Cassandra, to actually follow an anti-pattern. Because if you make it seconds, and that's obviously a little bit overly naive, you know, you'd think more you'd make it, you know, minute or week or year. But if you did make it too small, it's very easy to fall into this kind of multi-partition query, even when you were following like the best principles, the best way to model your data in Cassandra. So here we would be falling into the same problem as our staff member example. And just to say that even if you end up doing this and you keep this down to a good number, say 2 or 3 partitions, you probably want to consider and benchmark executing these as, parallel asynchronous queries rather than, doing it all in one big query. Just for the reasons we've already mentioned, so that retrying is less of an issue. And obviously you get the benefit of using multiple coordinators. So that's it for client-side joins and multi-partition queries. So the kind of takeaways are, we need to denormalize. We need to put things into user-defined types rather than separate tables. And what I find is and this is going to be a trend throughout this entire webinar, is I'm going to show trace. Because pretty much if you're using a multi-node cluster and you're constantly looking at trace, you'll be able to identify when, your queries are using too many nodes. And that's where you can predict that these queries won't scale. Okay, so the next thing we're going to talk about is batches. Batches are probably one of the most misused feature of Cassandra, or misunderstood. Because when I came to Cassandra, I was used to using batches in relational databases. And essentially, they were pretty much always a performance gain. I can group together and put multiple things in the same transaction and you get much higher throughput. However, that's certainly not always the case with Cassandra. They sometimes have a use case for performance, but most of the time it's different. So we're splitting it into two sections. We're going to talk about unlogged batches first, then we're going to talk about log batches. And the whole idea of this is not to say don't use them, is to make you understand how they work under the covers so you can make an educated decision about whether they're going to fit your use case. Okay? So what are unlogged batches for? So very similar to a relational database, it enables us to send multiple statements to the Cassandra server in one go. Now, that probably sounds like a great idea. You can amortize the cost of the overhead of talking to Cassandra and send everything in one go. And we're going to see how that's going to look like, for our customer events type example. And we're going to look at some examples using the DataStax Java driver. Don't worry if you don't come from a Java background. The code is very similar in most of the other Cassandra drivers, especially the ones produced by DataStax. So we can start off with some code that looks a lot like this. So assuming we've prepared the statement in green at the top of the slide here, and we've saved that prepared statement as insert statement, the text in purple, then each time we get a customer event, we can bind all the parameters. Now my assumption here is they're all stored in this Java object customer event. Then we can set the consistency level, and then we can execute that statement. But of course, with performance in mind, you might think, yeah, I'm going to put these in a batch and increase my performance. So the code doesn't change much. What we've done to the method signature is we've actually started taking in a variable number of customer events. So if you don't know Java, those 3 periods means that we can pass in many of them, essentially an array of customer events. And what we do is we create a batch statement, type unlogged, we loop around, we add all the events to a batch, and then we execute all them. Okay, so under the covers, it's going to send all of the inserts to that event. I'm sorry, there's some feedback. I'll start this one again. So under the covers, this is going to send all of the inserts to the customer to Cassandra.
Hey, Chris, we're getting an awful lot of feedback. Are you dialed in via your phone or via the computer?
I'm dialed in via the computer.
Okay, we're getting an awful lot of feedback, so I don't know if it's your microphone.
Has that just started, is it? Because I just started hearing it.
Yeah, it's just started. Seems to have cleared now.
Okay, I won't move. Okay, so what we're going to try and do is understand whether this is a good idea. And I'm going to do it with the example of inserting 8 records into an 8-node cluster, and we're going to assume that they're evenly distributed around the cluster. We're not going to worry about replication because the animation would get a bit too busy. So we'll just assume a replication factor of 1. So what the driver is going to do for this unlogged batch, it's going to select a coordinator, it's going to send them all in one go, and then it's the coordinator's responsibility to break that batch up and then start sending it out to all of the nodes in the cluster, depending on where the replicas are. Now, there are some reasons why this is not a good thing. This might be a good thing when you're running a single nodes database, okay? But what we've essentially done is circumvented some of the cleverness inside the driver. So the first thing is, look at how many nodes in this example need to be up and responding for this entire query to succeed. If you do big enough batches, what you'll essentially be doing is making sure that every node in your Cassandra cluster has to be up for this to be successful, okay? So that's the first disadvantage. Because essentially means that if only a few nodes in our cluster are overloaded, queries will start failing. The second problem is the fact, look at how much work the coordinator's got to do. If we start sending these big batches, what's going to happen is that the coordinator has to keep track of all of these messages that it's sent out and when they acknowledge that write's been accepted. So we've got quite an unbalanced customer node here, which is the coordinator. If you use batches wrongly, you'll often see nodes in your cluster having much higher, say, CPU usage, okay? The other problem is it completely ruins the performance of the token-aware driver. So the modern DataStax drivers don't send it to a random coordinator anymore, or they don't do, say, a round-robin policy. The default is to send it to a node which actually owns the data. So if we see what this looks like, if we were to not do an unlocked batch, but we were to just asynchronously do all of these 8 inserts separately, what it would look like this. The client would be sending it directly to the correct node. And we'd go around, and then we'd be done. And this is so much better because we're taking advantage of the token-aware policy. Our cluster is evenly balanced. We're not overloading particular nodes because they're coordinators for large batches. And if a single one of these inserts fails, we get to retry an 1/8 of the work, okay? Whereas previously, we'd have had to retry the entire batch. You're probably thinking, why would you ever use them? But there is a use case, and you may get a performance gain if you do. And the use case is this. So if you need to insert a lot of rows for the same partition, so if you see, what have we changed here? This code looks very similar, but it's actually, there's a little difference which makes a huge difference. And this is the fact that we're only going to store, we're only going to batch things together that have the same customer ID. Now, if you remember, the customer ID was the partition key. So here, what we've done here is we're building a batch for things for the same customer. And then, apart from that, it's virtually the same code. We're looping around them, we're adding them to the batch, and then we're executing them. And just to finish our section off with a little animation, it's going to be as simple as this. With the token-aware policy, it's going to go directly to a coordinator that is a replica for that partition. It's going to store it, and then it's going to respond. So you can suddenly see how suddenly you do get a performance gain from this. Okay, so that was unlogged batches. But logged batches, which were introduced in Cassandra 2.1, have virtually the same anti-pattern, but quite a different use case. So if you haven't used these before, some people refer to them as atomic batches. I prefer logged batches, okay? Because in a distributed system, it's very hard to achieve any form of ACID transactions or atomicity because you're trying to get nodes that have or computers to agree on something which might be on the other side of the world. But Cassandra does have a feature which can help you out, and that's logged batches. That's basically saying that if you need to keep some tables in sync, or you've denormalized and you need to make sure they don't get out of sync somehow, then Cassandra can actually put extra effort into making sure that everything in the batch succeeds. This is achieved, and we'll show this via an animation again, by first distributing the batch to a set of nodes called a batch log, and before actually writing them. But of course, this adds a lot of overhead. These are somewhat slower. If you're constantly benchmarking and you move from unlog to log batches, you're going to see a performance hit. The code is virtually the same. So, you know, apart from the type of batch. So here we've removed that first partition, and we've just gone to, you know, any number of customer events. And we're going to say it's of type log, and then the rest of the code is the same. Let's see what's actually happening under the covers to see whether we actually want to be doing this. So because we're going to go with eight writes again, evenly distributed, same as the first example. You know, our driver is going to select a coordinator. It's going to send all 8 there. Now, before the coordinator begins to write, the first thing it does is it collects a couple of nodes in the same data center, but ideally on different racks, and it sends the batch to them. These aren't readable yet. This hasn't started going through the normal write process. Okay, so once it's got it onto the batch log, then it's going to actually attempt to do the write. So then we'll start sending the write out just as before. Now, I haven't got this in the animation, but imagine that the coordinator were to fail right now. The big advantages of log batches are if the coordinator fails, one of the other batch log replicas will take over and finish it off. So that's the use case. But if you try to use these for a performance gain, then you're going to see we're actually doing vastly more work than unlog batches. Okay? So we're going to even see worse performance. And of course, the use case is this. It's not for inserting lots and lots of rows in the same batch. It's for when you want to keep 2 tables in sync. So with the table, the customer events table that we've been working with, we're only able to query this by customer ID and then filter it by time. But if we have the requirement to want to be able to query it by, say, staff ID as well, then we'd store it twice. We'd denormalize. And if you had a requirement that you needed to keep these in sync, then what you could do is create 2 prepared statements, one that inserts it by customer ID, another that inserts it by staff ID, and put these 2 things inside a log batch. And then what Cassandra would do is really attempt to get both of these written, even if there's failures in the coordinators, etc. But you've always got to consider whether this is worth it, because is it better to be slightly out of sync or have to have some recovery mechanism if the odd query fails, but to take this like 30% performance increase? That's a decision up to you, and you should benchmark both. So that's it for batches. Hopefully you'll think very carefully before you decide to use a batch again. Okay, they've got their use cases and they're really good features, but you know they're often misused because people assume they're going to get performance increases out of them. So the next thing we're going to talk about is mutable data in distributed systems. So apart from denormalization and schema migration and things like that, questions around, you know, the consistency of mutable data are probably what I get asked the most, okay? And it's a pretty hard problem, and we're going to go through a pretty naive example to show you just how bad it can be if you do this incorrectly. So if you're running if you're running a single node database, so a relational database, or perhaps you're running a master-slave system, or even a master-slave sharding system. Now, writes all go through a single point in these systems, which gives you, you know, good consistency. It also gives you a single point of failure and a single point of, say, your bottleneck. Cassandra doesn't work that way. You know, you can issue writes to any node in the cluster, but if you then decide to model your data so you have mutable states, then you're going to run into some problems. And most of the examples you'll find online where people say, hey, Cassandra loses data, it's normally an example that's nearly as naive as this. So what's going to happen here if we were going to store account information, so people's balances? What we'd have to do, it looks like Luke's overdrawn, Chris has got loads of money, and Patrick's not doing so bad. Okay, but if we were going to model our data like this inside Cassandra, we'd have to read this and then write it back and say, add £50 or, you know, take money away. And that's really not a good idea. Doing any read before a write in Cassandra normally means you're falling into an anti-pattern, okay? because Cassandra uses last write wins. If you've read the Dynamo paper or you've used systems like Riot, you've probably come across vector clocks. And in key value stores, vector clocks are very important because you're very likely to have a conflict. But in a wide column database like Cassandra, what you generally want to do is just not model the data so you have mutable state. And let's see how we do this. Now, the reason I haven't continued to use the customer event example because it was already modeled immutably. There was no mutable state there. We constantly appended new events. And we can do exactly the same thing inside this accounts example. So what we can do here is rather than store a mutable variable, which can be just as much of a problem on a single computer, what we're going to do is store the events. We're going to log the deltas. So here we have a partition key of customer, and we have a clustering column of time. And we've used the brilliant type, which is a time UID. So here, as we add deltas to our accounts, we're never actually going to update a column. And Cassandra is last write wins on the column. So it's not on the row, it's not even on the partition, it's every single column. And with this data model, we're never actually updating a column. Now, the complexity that we have to deal with here is the fact that it becomes more complex to read this data, because what we're going to have to do is calculate the balance when we read it. However, we're going to be storing all of these deltas on order on disk and doing a sequential read. The read from Cassandra is still going to be quick. But eventually, as the number of events gets very large, then, of course, it's going to slow down. So we'd steal more things from event sorting where perhaps at the end of each day or week or month, depending on the frequency of your data, you would snapshot this and roll it up. So you'd only need to use this pattern of, say, a log structured data storage on the very recent mutable data when you're getting new events. So quite a small section, but quite a different mindset to deal with when you're storing data in distributed databases without, say, a master or a single point. Okay, so you're always looking to avoid updating mutable data. Now, Cassandra does have other features which means that you can get away with mutable data. One of which is lightweight transactions, or as I prefer to call them, compare and swap. That's where you can actually read a value, say a bank balance or a number of tickets sold, and then you can update it, but only update it if the value hasn't changed, okay? But the thing is, if you think how that's going to be implemented under the covers, Cassandra suddenly has to then, rather than just, append it onto its, into the commit log and just go to a mem table, it's going to have to coordinate amongst all the replicas, okay? And it's going to be much slower. In the order of, it has to do around 4 round trips between all of the replicas for your data, and that's in the uncontended case. So in general, lightweight transactions are really good if you're going to hit that part of your application infrequently. But if you want that scalable performance, you probably want to move over to a more immutable data model. Okay, so next anti-pattern. So this time we're going to talk about crazy retry policies. Or what they normally boil down to is understanding failures properly. So failures in Cassandra are quite different to failures in, say, ACID relational databases. And I have fallen foul of this a number of times. I actually combined a couple of the anti-patterns. I used a multi-partition query, which meant that my queries failed more often. And then I didn't quite understand how failures worked when I started with Cassandra. So I then had what I would classify now as a crazy retry policy. So I ended up doing the double whammy of anti-patterns. But let's try and avoid doing this in the future. So we're only going to talk about writes just because they're the mutating ones, they're the dangerous ones. What we're going to try and do is really understand what a write failure really means in Cassandra. So we're going to assume that we're going to write some data, and we're going to write this at quorum. So the first misconception we often get with Cassandra is that your consistency affects how Cassandra writes data, which is not the case. Regardless of what consistency you write the data at, it's going to send it to all 3 of the replicas, okay? And some of those replicas might respond in time. So because we've got a replication factor of 3, and we're going to write this at quorum, then we want at least 2 of these replicas to come back to us and say, yep, I've written the data. If this doesn't happen, if, say, replica 3's come back to us, but replica 1 and 2 have timed out, then what the coordinator is going to do is it's going to send a write timeout back to the application. Okay? So the really important thing to note here is Cassandra does not roll back, okay, like you might expect if a transaction fails in a relational database. So the situation we're in here is that replica 3 has the data, okay, it is stored. Replica 1 and 2, we don't know because they didn't respond to us. The coordinator, if you've got hints enabled, will have kept the hints, and will, you know, if they do go down and come back up, we'll get the hints when it comes up. But what I accidentally did when I first started working with Cassandra was just put a blind retry policy in. And then I moved to, say, a downgrading retry policy, which is in some of the drivers. And when you think about it, if we've written this at quorum and we've actually got it onto one of the nodes, there's not much point retrying that write at 1 because it's already written to 1. And if you're using a DataStax driver, the driver is actually going to tell you this. So when you get a write failure back, all write failures are not equal. Some of them, they're all going to include this information. It's going to include how many acknowledgements it got, how many it required based on your consistency level. So you actually know, you could already know, you could have a clever retry policy to say, actually, if I did get onto 1 or 2 nodes, I don't need to retry. I only actually need to retry the writes if I got 0 acknowledgements. It becomes slightly more complicated when we start working with lightweight transactions or compare and set and batches. Hopefully we really understand how batches work now because we've spent quite some time on batches. But essentially what Cassandra and what the DataStax drivers will tell you is which part of the batch failed. So if you remember back to the animation, if we're doing a logged batch and we failed to get it out to the, we failed to get confirmation that the batch log replica has worked, okay, we'll get a write failure type of batch log. So we know then we should probably retry because we don't know that the batch log replicas got it and are going to be retrying it in the background. However, if we got past that phase, we got it onto the batch log replicas and we're going to get a write type failure of batch, which essentially means that it's very unlikely that you're really going to need to retry. You'll have 3 nodes in the Cassandra cluster constantly trying to apply this for you. The only time I could possibly think that you might want to retry this is if that node desperately needs to read its own writes and you don't mind taking the performance hit. For unlocked batches, you're very much in the same case as just normal writes. One last thing to talk about before we move on is idempotency. So there are certain types of writes in Cassandra that aren't idempotent. And they are in the minority. So virtually every write in Cassandra is idempotent. It's why the drivers can retry, etc. However, there are 2 cases when they're not. And you should be very careful about doing retries or even using these particular features of Cassandra for very critical where it has to be exactly right. So one is counters. So if you retry an increment, it's obviously going to increment it twice. The other is lists. So if you're trying to append something to a list, if you accidentally retry that when you shouldn't do, you're going to end up in the list twice. So you shouldn't be using counters for exact numbers, like when the accuracy is of prime importance. And you should always prefer to use sets over lists. And beware that sets in Cassandra are ordered, so you don't need to worry about that. So we're on to the next one. So Cassandra is a queue, which I find quite funny because people try and do it a lot. I've tried to do it. And when I used to work on queuing software, people tried to use it as a database all the time. But it's a more general answer pattern. You don't have to be thinking, I'm using Cassandra as a queue to fall into this. What you could be thinking is, at any time which you delete a lot in a partition and then do slice queries across that partition, you can fall into this anti-pattern. This is really quite a well-documented one, so I'm not going to spend much time on it. and there's a couple of blogs here which you just go and read. For this anti-pattern, I didn't create my own content. I actually took it from the top one, the DataStax tech blog. I figured I worked for DataStax, so I was allowed to do that, and there wasn't much point, spending time generating my own content for it. One of the reasons I'm still talking about it, though, even though it's quite well documented, is even with some experience, I still tried to do it at one point. Didn't get anywhere near production, but at one point I had an application and it was running in 2 data centers. And then I had another data center which didn't have the application in, but I wanted to send messages from between the data centers. And obviously I was thinking, should I just do something synchronous over HTTP, or should I bring in some queuing software? I thought I already have this technology which is brilliant at cross-data center replication. Perhaps I should just expand the Cassandra cluster out to the new data center. There's a reason why this is a particularly bad idea, and it's because of the way that deletes work in Cassandra. So, as you know, Cassandra doesn't read then write. Okay, so if you're going to do a delete, we don't go into the mem table or the SS tables on disk and try and delete it. What we actually do is put a marker to say this column is deleted. So when you come to read it, it sees that there's what's called a tombstone with a later timestamp than the last value, so it knows it's deleted. The bad part of tombstones is if you have a buildup of them, because they are kept around for some time, then you can spend more time scanning over the tombstones than you can actually reading your actual data. And this becomes very apparent if you have a data model which looks like queuing. So let's have a look at how that would be in CQL. So imagine we had a queues table. We have a name of a queue, and that's the partition key, and we also have a enqueuedat, which is our time UID. So they're going to be ordered on disk in a FIFO way, so a first in, first out. And of course, we're always going to read from the back because we want the oldest message. Okay. Once we've read the message, we're going to delete it. So that's a very queue-like data structure. Now, even if you ignore the race conditions of reading and then deleting and that type of thing, you have to realize that what you're going to do is be building up large number of tombstones at the start of this partition. And if we're doing this query, this one at the bottom of the slide here, where we select from name equals queue, but we limit it, so we just get one of our messages back, we're going to be reading over every tombstone that ever existed for that queue. Now, if you know about GC grace period, the default for that is 10 days. So essentially, we're going to be reading through 10 days worth of tombstones for every single read. This is one of these anti-patterns where it'll work for a while, but as your application, has been in production for a while, you'll be building up these tombstones, and your performance will be getting worse. We're going to look at trace again to see this in action, because as I've said, most of these anti-patterns are really obvious in trace. So this time it's a 3-node cluster running locally. It looks like we've inserted and deleted nearly 20,000 messages in our queue. Okay, and if you see, to read one record, to read one column, which meant one message inside our queue, we've had to scan over nearly 20,000 tombstones, and not surprisingly, that's taken some time. So that's the reason why Cassandra isn't too suitable for this type of data modeling. Now, there are times, of course, I'm not trying to say never use deletes. What we're trying to avoid specifically are lots of deletes and then these like slice or range queries over them. And there are a number of ways to avoid this. Okay, so let's say you do need a data model which is similar to this. So the first thing you can do is make sure you don't remain in the same partition. So rather than, in our previous example, staying in this the partition for the queue name, what we'd actually do is we'd put some kind of time bucket in there. So if every hour or year or month, whichever, depending on the frequency of your messaging, you'd be moving partition. So we'd have like, queue Chris for the last 10 minutes or the last day, etc. The advantages of this is we don't go anywhere near the old tombstones. The other thing we can do is give Cassandra a big hint, because if we know we're reading data in time order, then we know that the next message we get is probably going to be newer than the last one. And we can actually tell Cassandra about this by adding a, say, what do you call it, a greater than inside our query. So in the queuing example, it's the last bullet point here. We can actually say in QDAP is greater than, say, 5 minutes ago. So this is a time UID. And that way, that gives Cassandra a hint, and then it can very efficiently avoid scanning over all of the partition, all of the tombstones. Okay, so we're nearing the end. We're on to our last anti-pattern. So this is some people's favorites. So if you've been around Cassandra for some time and you've been on Stack Overflow or the mailing list, no doubt at some point someone has told you, whatever you do, use a secondary index. You probably think to yourself, why? It sounds like a really cool feature. So what we're going to try and do today is explain exactly how secondary indexes work under the covers, so you can really understand why most of the time they're not going to be a good idea, and they're probably never ever going to give you the performance that you could get from denormalizing your data. So we'll go back to our favorite table, the customer events table, and we'll go back to the added requirement. So before we're allowed to, with this data model, we're allowed to query by customer ID. But what we really want to be able to do is also query by staff ID. If we try and query by staff ID, what's going to happen is we're going to get this error message back. You've probably seen this in CQLSH. It says no index columns present in by columns clause with equal operator. So surely the logical thing to do, because it says there's no index columns, is to create an index. So that's what we do. So we'd actually, do create index on staff ID. But let's try and work out how Cassandra implements this under the covers and why we're not going to get particularly great performance. So here's some data. I've cut out most of the other columns. The only ones I've left in are the partition key, the clustering column, which was time, and the column that we're interested in indexing by. Okay, so we've got the staff ID. We have a couple of partitions. We've got CH, Beatty, and Rusty, and a couple of staff members. So we've got Trevor and Bill. And what Cassandra is going to do under the covers, it's probably not too surprising, is reverse this for us. So it can actually, it can work out which partitions are for each staff member. So here instead of going from customer ID, the index table goes from staff ID to customer ID. So if you query by Trevor, you can go into this secondary index table and see, oh, the CH, Beatty, and Rusty have records for Trevor, so I better go and look at those partitions. But alarm bells should already be ringing here, because as soon as you use secondary indexes, then the chances are that you're going to end up under the covers doing multi-partition queries. Because unless you've got a one-to-one mapping, unless we only had the same number of staff members as customer IDs and they happen to be one-to-one, then when we look up by Bill, we're going to end up having to follow up that query, internally that is, to look up Rusty and CH Beatty. So we've already kind of discussed the disadvantages of this. It suddenly means our query is going to be reliant on many nodes, and it's going to be much slower, and it's going to be much bigger if we try to retry it. But that's not the only downside to secondary indexes. The other reason that they're really quite bad is the fact that they're distributed differently. They're not like a normal table. So in a normal table, we hash the partition key and we find out which node it goes, and assuming a reasonably even distribution, we have roughly our table split equally across all of the nodes. Now that's not how secondary index tables work, and we'll talk about why in just a moment. But how they're really stored under the covers is on each node, there's only the entries for the secondary index table that belong to the partition on that node. Now, I've never been very good at explaining or understanding that in words. It's always so much easier, I think, with an example and with some pictures. So that's what we're going to do. So we're going to assume a really simple two-node cluster, A and B. Same data as we've been looking at, so the same index table. We're going to assume a replication factor of 1 just so we can concentrate on how secondary indexes work. So it turns out that CH Beatty maps to node A. and Rusty maps to node B. So then we can work out which parts of the index table belong on each node. So for the partitions, for the staff members that map to CH Beatty, those bits live on node A. For the parts of the secondary index that map to Rusty, they live on node B, okay? And the problem with this is if we start to issue queries against this cluster, which don't include the partition key, what Cassandra has to do is it has to go look around all of the segments of this secondary index table. So you can imagine it has to go to virtually every node in the cluster. So it's going to be extremely slow. The reason or one of the reasons, a theory of why it's implemented like this, is simply because, let's say they were distributed like a normal table. Imagine that we only had 2 staff members, but tens of millions of customers. What if we distributed that table normally, then we'd only end up with 2 partitions. You know, say that we only ever had Bill and Trevor for millions of customer events. We'd only end up having 2 partitions inside the index table, and thus it wouldn't scale. The best way to understand this is by far to see trace. Okay, so if you're really keen, I've got some homework for you, and we might be able to send you out a prize depending on where you are in the world. So what I'd like you to do is install CCM. So either go to the website or go to DataStax Academy and work out how to install it. Spin up a 6-node cluster. Okay. You can obviously take the schema from the slides. I've put them on SlideShare and I'll tweet that out. So you've got the customer events table, and I want you to create the secondary index. On a hidden slide, which you'll get if you download the slides, there will be the data that we've been playing with in the example. So go and insert that. The next thing I want you to do is do these 2 queries. So we're going to use the index both time if you see A and B, okay? So we've got staff ID equals Trevor as one of the queries, and staff ID equals Trevor and customer ID equals CH Beatty for another one. And what I want you to do is just on Twitter, just send me an explanation of roughly how many nodes in the cluster would be used and an explanation of why, okay? Because these 2 queries are really different. One is going to be a few lines of trace, one is going to be pages of trace, okay? And if we can, the first person who sends me an answer will hopefully send out some swag, but no guarantees. Of course, the way you would really solve this problem is denormalization. And the massive reason why this is always going to perform vastly better is as soon as we denormalize that data, we store it by staff ID. All of that information is suddenly sequentially stored on disk. So we're not even having to go to multiple nodes. We're not even having to do multiple disk seeks. So it's really, this is a much better way of doing it. But of course, people get sick of denormalizing. So there's a lot of buzz around a certain JIRA in Cassandra at the moment called global indexes. And, Cassandra is an open source project, so you can go and contribute. I don't necessarily mean to the code, but I mean to the discussion that's happening here and maybe put your use case down. Because, they're going to have to solve that problem of the fact that the index can't end up with too big a partition. So hopefully I've convinced you that you should really think carefully before using batches or secondary indexes. So we're coming to an end there. So we've covered quite a lot. Okay, I've actually spoken for a bit longer than I thought, or the intro was slightly longer. Well, we've gone through batches and joins. Hopefully, if you really understand how secondary indexes work, I'm going to follow this up with a blog explaining secondary indexes with trace and detail. But hopefully you're not going to fall into some of these problems now. So thanks for listening. Any questions we don't get time to now, I'll stick up a blog, so we will answer them all. It just might take a little bit longer. Most of the anti-patterns that when I've been building up this slide deck, I wrote a much more detailed blog post about, so you can go and read in more detail about what I've been talking about. Again, if you've got any more questions down the line, just ping me on Twitter. And I would really advise you to check CCM out and go to the DataStax Academy. If you want to learn more about how Cassandra is the right path, then really do that. So on that note, in the very British way, we'll keep calm and use any time for questions.
So, Chris, there are absolutely loads and loads of questions in here. I don't know whether we should start and get through a couple. So you let me know if you're game for a couple.
Well, let's go for a couple, and I don't promise to be able to answer them, but I'll find someone who can and get back to people.
Okay, how about this one? This is one that maybe we can get through. How would I go about solving limit offset queries without having to skip rows programmatically? For example, taking a simple page 2 customer table.
Sorry, did you say how to do limit queries on a set?
How would I go about solving limit offset queries without having to skip rows programmatically?
So at the moment, you can't. So you can only query things in Cassandra which are stored in order. For the person who asked that question, I'll ping you another JIRA, which is user-defined functions, and at that point, you're going to be able to actually execute some code on the Cassandra side, which is going to be able to like filter parts of partitions, so you won't need to store the data over. So stay tuned for Cassandra 3, which is sometime in the next month or two. Not sure on release dates for that.
Okay, next one, and I think we've got time for maybe 3 more. There are times when data simply cannot be written simultaneously and therefore must be joined at a later time. What do you recommend for joining needs? An external tool such as Spark SQL or something else?
So Spark is a fantastic tool for doing that type of thing, but bear in mind it's more of an analytic, slow type of query when you're doing those type of joins. So you're not going to get these single-digit milliseconds. So if it's a one-to-one joining, then yes, do it inside your application, rather than build in a separate tool. If it's something that you've realized later down the line, then what Spark can be great for is rebuilding a new table based off old tables. So rather than doing the join in your operational system, do the join and write it back to Cassandra so that your operational application can read it exactly as it is.
Okay, great. I'll answer everyone who's asking whether the slides will be available. So within about 48 hours of the webinar, we post the video of this so you can replay it and the slides along with it to Planet Cassandra. One last question, Chris, and thank you so much for taking the time today. In order to emulate a queue without falling on this anti-pattern, can I use the new date-time compaction strategy and TTL?
The thing is, if you're doing that, that certainly helps because the date-time compaction massively reduces the overhead of deleting old data. So it just drops away entire SS tables. But if you're trying to build like a high throughput queuing system with Cassandra, you're still going to be reading over a huge number of tombstones. So it's still going to be slower. The only thing you can really do is like move partition really quite quickly so you're not reading over the tombstones. But there's very good queuing software out there. So.
Okay, great. Thank you. Thank you very much, Chris. Really appreciate your taking part today. And we'll look forward to your blog on the questions that there are absolutely loads of them. You've probably got 50 questions to get through here. So thank you, everyone. We look forward to seeing you next time. And keep your Cassandra learning going, either by joining us at a Cassandra Day. You can check out the cities that will be in on DataStax.com. We have free online instructor-led training. Again, you can find that on DataStax.com. And then if you want to take some self-paced learning courses, you can visit DataStax Academy for those. And then loads of great content on Planet Cassandra. So if you're interested in taking your learning forward, definitely have you covered. Thank you, everybody.